For decades, real estate search has relied on traditional relational databases. These systems use strict SQL filters that demand exact matches for attributes like price, city, and bedroom count. If a user's query doesn't perfectly align with the database schema, the system shatters its ability to return relevant results. Modern users, however, do not think in Boolean logic. They search using unstructured, natural language phrases. A home buyer is far more likely to ask for a cozy apartment with a fireplace and Trudeau's than to select a series of isolated checkboxes. Processing that intent requires artificial intelligence, but you cannot simply route a user's search string directly into a large language model and expect it to query a standard database. The model has no persistent memory of your inventory, and standard databases cannot parse conversational syntax. Building a true AI search engine requires constructing a highly specific architectural pipeline. It demands a strict separation of three distinct phases: semantic ingestion, hybrid retrieval, and business logic scoring. When developers fail to build these strict boundaries, their search applications either hallucinate inaccurate properties or the query times out while trying to scan thousands of records at scale. To understand how to build this correctly, we will deconstruct Agensa. Agensa is a property platform engineered for the Cyprus market, designed specifically to solve this semantic search problem while maintaining response times under 200 milliseconds. This tech stack utilizes a Nuxt 3 frontend, an Express 5 backend, and a Postgres database. The critical dependency here is pgvector, an extension allowing rapid vector operations. It stores 4,096 dimensional embeddings, mathematical representations of concepts, to instantly calculate similarity. Installing the database extension is straightforward. The true engineering challenge lies upstream, taking literal property inventory and transforming it into mathematical vectors that actually capture user intent. That transformation happens during the first phase of the architecture, ingestion and enrichment. When an agent uploads a property, the raw database row contains literal Boolean features, a true or false flag for fireplace or solar panels. You cannot embed these raw flags directly and expect high-fidelity search results, because the math will only understand the literal words, not their implications. This flow diagram illustrates the solution. The raw property record is sent into a backend function called the Property Summarization Service. This service engineers a latent semantic space, essentially building out the hidden contextual meanings of a property before any mathematical embedding takes place. It does this by mapping literal features to broad semantic concepts. A Boolean flag for fireplace triggers the service to inject related keywords into the property profile, such as warm, cozy, and winter-ready. Similarly, if the property features a gated community, the service proactively expands that single term into secure, exclusive, and family safe. The service then evaluates those newly generated concepts and injects overarching lifestyle context tags. It aggregates all of this enriched text into a single unified text block called a search summary. Now that the contextual data exists in plain text, it is passed to the embedding service. This component calls out to OpenRouter, an API gateway for large language models. OpenRouter analyzes the enriched search summary and returns the 4,096-dimensional vector embedding. That dense array of numbers is then written directly into the embedding column of the Postgres database, alongside the original property record. From an operational standpoint, this generation step is highly efficient. Generating the embedding costs roughly 2 cents per 1 million tokens, and the API response completes in 100 to 200 milliseconds. By forcing enrichment during pre-computation, the database mathematically understands the feeling of a property long before a buyer presses the search bar. With the inventory fully indexed, we shift focus to the backend service to examine the exact life cycle of an incoming user query. Consider a scenario where a user submits the text, "Cozy 3-bed with fireplace in Trudeau's." This execution chart reveals how the search service handles the request. To maintain a sub-200 millisecond response time, the system cannot process the text sequentially. It immediately splits the string into 2 simultaneous parallel tracks. In track A, the raw query text is sent directly to OpenRouter. This generates a 4,096-dimensional query embedding, formatting the user sentence into the exact mathematical shape used by the database. Simultaneously, in track B, The identical text is routed to GPT-4 through a dedicated AI service. This node's job is to extract structured, logical intent from the messy human input. Track B successfully parses the query into distinct categories. It identifies exact numerical keywords, isolating 3-bed, while simultaneously categorizing abstract lifestyle preferences, tagging the query with mountain living based on the mention of the Troodos region. This parallel split equips the downstream system with two vital tools: a fluid mathematical shape for broad semantic matching and strict logical parameters for precise filtering. The lifecycle moves to the retrieval phase. The backend takes the mathematical vector generated in Track A and queries the PG vector database. Looking at this conceptual sequel, you can see the PostgreSQL cosine distance operator, represented by the less than equals greater than symbol. Cosine distance measures the geometric angle between vectors. By comparing the query embedding against every property embedding, the database calculates a precise similarity score. This mathematical comparison executes instantly, returning the top 50 most semantically similar properties from the inventory. But pure vector search has a critical limitation. It struggles to enforce hard numerical constraints. The math measures proximity of concepts, not absolute rules. For example, a 5-bedroom villa might return a high semantic match for a 3-bedroom query, simply because both listings share extensive vocabulary about family living, fireplaces, and mountain views. To solve this, the architecture implements a secondary relevance scoring pass. It takes the top 30 results from the vector search and routes them directly to GPT-4. GPT-4 evaluates those 30 properties against the strict JSON intent parsed back in Track B. It cross-references the literal bedroom counts and specific constraints, assigning each property a final relevance score from 0 to 100. The system enforces a strict filtering threshold. Any property that scores below a 40 out of 100 is deemed logically irrelevant and is dropped from the results payload entirely. Before the results are served, a final business logic layer applies an advertised boost. Paying agents receive a base multiplier of 12 points added to their AI score. This ensures their listings rank slightly higher in the output without overriding the core relevance filtering. Effective AI retrieval functions as a hybrid system, combining fast vector math for broad initial recall with a secondary LLM for nuanced logical precision. While this hybrid pipeline is robust for textual descriptions, examining the platform's mapping feature exposes a critical architectural flaw in how spatial data is handled. This map projection illustrates the UI presentation layer. The front end utilizes the Mapbox Search API to locate points of interest, like grocery stores and schools, displaying them within a 2-kilometer radius of a given property. The system generates this bounding box by utilizing a standard geographic approximation, calculating that 1 degree of latitude equals roughly 111 kilometers, and drawing the boundaries accordingly. Because this spatial data is fetched dynamically on the client-side UI, it exists solely in the presentation layer. The core search engine cannot see it. The consequence of this isolated data is severe. If a user types apartment near a supermarket, the vector search pipeline completely fails to return an accurate match. It fails because those 4,096 dimensional embeddings stored in the Postgres database contain zero information about the Mapbox amenities. If the real estate agent didn't manually type the word supermarket into the description, the math has no way to calculate the proximity. Keeping spatial awareness isolated in the UI layer creates a disjointed user experience. The visual map knows contextual facts about the neighborhood that the back-end search engine simply does not. The solution requires shifting the Mapbox API queries backward, moving spatial awareness directly into the ingestion phase. This revised pipeline shows the new workflow. During property creation, the backend proactively queries Mapbox using coordinates to discover exactly what amenities are nearby. It retrieves counts of those amenities and injects that spatial data directly into the search summary block. This injection occurs strictly before the embedding service packages the text and sends it to OpenRouter for vector generation. Because the text now contains the phrase grocery stores within 2 kilometers, the resulting mathematical embedding inherently possesses the context of the property's spatial environment. High-performance semantic architecture synchronizes literal, spatial, and latent data into a single unified vector space at index time, a structure then unlocked by hybrid LLM retrieval at query time.